So my name is Mutsuhisa Sato from the Riken Center for the Computational Science. It is an honor to have such opportunities to talk about the supercomputer Fugaku. I'm going to talk about Fukaku and the mini-core processors A64FX we have developed with the industry partner Fujitsu. Flagship 2020 project is a project to develop our national flagship supercomputer. I'm deputy project leaders and team leaders of the architecture development team. This is the one-page slide to describe our project. Our mission is building our national flagship supercomputers and also developing the wide range of the application running on a Fukaku. The August last year, the K computer decommissioned and removed from the supercomputer room because Fugaku is installed in the same place. The last year, from the October, we got access to the test chip for the evaluation. At the supercomputing conference the last year, we submitted the result to the Green 500 using the 2-rack system installed in the factory of the Fujitsu. At the supercomputing conference in last year, we got #1 position in a Green 500. So we achieved almost 70 gigaflops per watt power efficiency. So it was a surprising result since the general purpose mini-core processor beat the GPU. Unfortunately, at the ISC this year, NVIDIA GPU A100 they exceed our result, but the #1 was the Japanese PFN MN cores AI chip. At the supercomputing conference last year, we announced the clock frequency of the A64FX chip as the 2.0 GHz. It can be boosted up to the 2.2. And Fujitsu announced their commercial version FX1000 and the cluster version FX700 using InfiniBand as a network. From the December last year, delivery and installation of the Fukaku was started, and delivery is completed in this May. This is the picture of the Fukaku. It is installed in the same room of the K computer was. If you have a chance to come to Japan after the COVID-19 disappear, please visit our centers in Kobe. At the ISC this year, we have submitted the result for 4 benchmarks, Top 500 HPL, HPCD, HPLAI, and Graph 500. This is the result. As you see, we won #1 in all 4 benchmarks. The result to the 4 times faster than the second system in all benchmark. I think it indicates our system is good for wide range of the application, and this is what we think important about this result. The Fugaku system is already partially used by the early access program users. The system is used for researchers to fight against COVID-19. For this program, we have the 5 projects now. These 3 projects are medical and pharmaceutical research. Professor Okuno in Kyoto University is working for large-scale MD simulation to find a drug candidate for COVID-19 target protein. And Dr. Sugita at the Riken is working for the MD simulation to analyze the spike protein structures. And Professor Mochizuki at the Rikkyo University also working for the MD simulation to analyze the protein of the COVID-19's the virus. And the 2 projects are for societal pandemiology research. Professor Tsobokura, Riken and Kobe University, is working on how the virus droplets fly in many kinds of the environment, such as the office room or classroom. He is using the CFD simulation to simulate the droplet. And Dr. Ito is working for pandemic simulation using the large-scale agent simulation. As I told you, the flagship 2020 project has the mission to develop the application. At the beginning of our project, our government identified 9 priority issues as a target science and organized the project for each area. The first one is the drug discovery and the genome analysis. The 2 areas is for society with health and longevity. And 3 and 4 is disaster prevention and the global climate. And for the disaster prevention, this group is developing the application for tsunami simulation and earthquake simulation. And this group is developing the global climate simulation. And next 2 is for energy issues. So the number 5 is for design of the efficient battery, and number 6 is designed for the very efficient wind power plant. And 7 and 8 is for industry competitiveness, and it includes the new functional devices and also innovative design and production as a process using the CFD and the structure analysis. And last one is the basic science, which is including particle physics and the astrophysics. 4 areas were added later as the exploratory issues. So this area is agent simulation for socio-economic phenomena. And last one is for the brain science and artificial intelligence. For co-design with application, we asked each project to provide one application as the target application for the co-design. This table lists the target application from each the project. The target application represents a typical program in terms of the computation method and the communication pattern. In our project, we defined the 3 KPI, key performance indicator, as shown in this slide. The first one is the power efficiency. We have decided the maximum power supply to the 30 to the 40 megawatt in our facilities. At the design phase, we set 15 gigaflops per watt for the DGEM as the target power efficiency. As a result, we got the first position of the Green 500. Second one is the effective performance of the target application. The application of the benchmark was not our priority. We expect 100 times faster than the K computer in some application. The K computer is a 10 petaflop system, so this is the kind of our definition of the exascale computing. We confirm 100 times faster than the K computer in MD application Genesis and NICAM LTKF, the climate simulation and the data simulation, the program. The third one is the easy to use. Our system has no accelerator like a GPU. Our system is just a shared memory system with the many core and a high bandwidth on package memory HBM. This makes the existing OpenMP MPI program ported easily. So we don't need any special the programming effort for the GPU. This table shows the target application and performance target against the K computer under the 30 to the 40 megawatt power consumption. As you can see, the performance of Genesis and NICAM LTKF was confirmed more than 100 times faster than a K computer. For another application, we expect 20 to the 40 times faster than a K computer. Let me describe the architecture of the CPU A64FX. The instruction set is the ARM version 8.2 with the SVE, scalable vector extension. SVE is the ARM SIMD instruction. And length of the SIMD is the 512 bits. And it has the 2 pipes for SIMD for each core. The number of cores is 48 plus 2 or 4 cores for running the operating system function. 48 core is divided to the 4 groups. Each group has the 12 core. This is a NUMA node, and we call this NUMA node the CMG, core memory group, because these core sharing the L2 cache and the memory controller. CMG is connected by on-chip network, and the PCI Express interface and the TOF network interface are integrated on the same die as the one chip. The memory is on-chip package stacked memory HBM2. We have only HBM2, no external memory. This is because of the cost. We cannot have the external memory for large number of nodes. The capacity of the HBM2 is the 8 gigabyte, and we have the 4 HBM, So totally memory capacity is the 32 gigabyte. We use the latest silicon technology, 7 nanometer FinFET. So, and it contributes low power logic design so much. The common programming model we assumed at the co-design phase was the OpenMP and MPI hybrid program. OpenMP process is running on each CMG and communicate another CMG with the MPI. But on-chip network support memory coherence, so you can run 48-thread OpenMP program using the all-core. This is the chip photo of A64FX. So as you can see, the core is divided the 4 group, and the 13 core is sharing the L2 cache. And the HBM2 interface and the TOFU interface and the PCI Express interface is integrated on a chip. So, and HBM2 is connected to the chip using the silicon interposer, using coarse technologies by TSMC. SVE is a SIMD instruction designed for Arm-SVE instruction set. The previous Arm processors has the SIMD called Neon, but SVE is designed for vectorization of HPC scientific workload. The interesting features of the SVE is the vector length agnostic programming. Instruction set does not depend on any vector length. The support vector length is stored in the register called vector length registers. Almost SVE instruction has the mask registers as operand, and it is used for parent predication. And it supports gather, load, and scatter store instruction is also. To design the exascale system, the power efficiency is a very important and critical factor. We have used the 7 nanometer FinFET technologies with the low power logic design. It contributes to reduce the power consumption very much. The processor has the mechanisms to switch off the many parts for power management. We have 2 floating point assembly pipe, FLA and FLB. We can switch off the FLB. It is the FLA only mode. And also we can change the clock frequency and memory access rate, and we call these switches the power node. So user can use these power node for power optimization. And energy monitors facilities can give the detailed information about the power consumption at the runtime. So we found the power reduction is not so large by just switching off the 1 floating point pipe, FLA only. So to make arithmetic works first at 2.0 or 2.2 gigahertz, we need standby powers for arithmetic unit. The echo mode stopped this standby power. It's reduced the power consumption more than 10 watt. This is the relatively very large. So, and we found 4 applications out of the 9 target applications selected echo mode for maximum performance under the limitation of our power capacities. And it's indicate that for memory intensive application, so we can reduce the floating point capabilities by switching off the one pipe. So this is valid even if we are using the HBM. For the network, we selected the TOF network, a 6-dimensional Torus network for the performance compatibility in large-scale simulation to the K computer. To co-design the network, the communication patterns are extracted and communication performance was estimated by the analytical model. The many applications have neighbor communication patterns or communication to the near nodes. So TOF and 28 gigabit link were sufficient. But some application is need the O2O communication. So we studied benefit and the feasibility of the additional dedicated O2O network, but it's not selected due to the cost. Instead, we decided to support 3 double precision reduction by TOF barrier network for QCD application. TOF interface is integrated on this the chip. The interface includes the 4 DMA engine called TOF network interface. So comparing to the K computer, the link speed is not so changed so much, but the number of the DMA engine were increased from 4 to the 6. So the injection bandwidth is improved. Since interface is integrated on a chip, latency is very low. This graph indicates the latency and bandwidth of the MPI ping-pong benchmark comparing to the K computer. As you can see, the latency is much improved, and the bandwidth is also improved almost 20% at the MPI level. As I told, everything is including the cores and the network interface and the memory are included in one chip. The chip is mounted on a board, and the chip is connected by the TOF network, not shared memory. The board is cooled by the water, and copper heatsink plate is attached to the chips and the optical interconnect. The board is mounted to the rack, and 384 chips are installed in one rack. This is a very dense system. The number of the nodes in Fugaku is more than 150K nodes. Fugaku supports a 3-level storage system. First layer is the SSD storage. So one of the 16 compute nodes, called the compute and storage I/O node, has the SSD about 1.6 terabyte. It is used for the cache for the global file system and also for the temporary file system. The second layer is the Fujitsu raster-based global file system, and third one layer is the cloud storage. This table shows the advance from the K computer to the Fukaku. Since K computer is started operation in 2011, so it is almost 10 years advanced. As for the core, 4 times faster than the K computer because of the SVE. And for the chip, the 24 times faster than the K computer because the AC64FX has the 48 core. So byte prop ratio is not so changed. Because the number of nodes is more than 150K nodes, so we have more than 7.6 million general purpose core. So values in bracket indicates at the number at the boost mode 2.2. So as you can see, single point peak performance at the boost mode is almost reached to the exaflops. Let me report some benchmark result of the A64FX using UK benchmark Cloverleaf and TLEAF, and the US benchmark and the Rulesh. We compare the performance of the A64FX with the Cavium, SanDisk2, and the Intel Xeon. This is the result of the Cloverleaf and the evaluation using the just one CMG without MPI. Left graph is the execution time, and right graph is the relative performance to the one thread of the A64FX. As you can see, it shows the good scalability by increasing the number of threads within the CMG. And the Broadwell has just 14 core per chip, so the one CMG performance is very comparable to the Intel one socket. So please note that A64FX has the 4 CMG in a one chip. It means that our chip is 4 times faster than the Intel one. This is the result of the TLEAF and evaluation of the MP program within one chip. We run the 4 MPI process for each CMG, and we measure the performance by changing the number of threads in the CMG. Upper graph shows the execution time, and lower graph shows the relative performance against the one thread, the A64FX. So as you can see, A64X performance is very good. It's almost twice of the Intel and SanDisk2. As you can see, speed up is limited to the more than 4 threads due to the memory bandwidth. The performance of the A64X is not always good. So this is the result of Rulesh, the evaluation of using the one CMG without MPI. So this is the benchmark program using the sparse matrix computation. One CMG performance is less than the SanDisk2 and the Intel one. We found low vectorization rate. The ratio of the CMD instruction is just a few percent. I think we need more code tuning for more vectorization using the CMD. This slide is taken from Fujitsu, and performance evaluation result using 7 open source software. OpenFOAM is the very famous CFD application, and also R-VNet is a famous application for the MO simulation. So, as you can see, A64FX is better than two-socket of the Xeon, thanks to the high memory bandwidth of the HBM and the SIMD. And this slide is about the power efficiency for open source software. For almost application, power efficiency of the A64FX is more than twice than Intel one. So this is the Fugaku software stack. The operating system is the Red Hat Linux. But if you want, you can use the microkernel called MC kernel. Using MC kernels, you can reduce the operating system jitters for the large-scale application. And for deep learning framework, Riken and Fujitsu and Arm is developing the deep learning libraries using the SVE. We are using the open source management tools called Spark. The many application is already supported by the Spark. So in summary, we are almost achieved our three KPI and the power efficiency and the effective performance of the application and easy to use. The Fugaku is proved to be the well-balanced system for several applications. So in this year, Fugaku partially used for the early access users, including a COVID-19 application. In the next year, from the April, public service will start. So now is the website is open for also for international users. If you are interested in, please apply to this call. The Fugaku development is almost finished. Now it is time to think about for the next system, next Fugaku. We did co-design with the target application, but I'd like to point out a kind of the dark side of our co-design methodologies. So we don't select any disruptive architectures like GPU, but instead it is easy to use system. But to get up more performance and more power efficiency, I think we need the application-specific accelerator. Otherwise, we should explore more rooms in general-purpose processors architectures for more performance and for power efficiency. Thank you for your attention.